Hi, my name is Michail Georgiou. I'm a practicing architect, a computational designer, and an associate professor at the Department of Architecture of the University of Nicosia in Cyprus, where I'm coordinating a postgraduate program in computational design and digital fabrication. The paper I'm going to present today is titled Metascapes: Architectural Quests in the Metaverse and is co-authored by my colleagues and collaborators Odysseas Georgiou and Iulios Georgiou. Before we begin, I would like to share that I'm glad to be here presenting our latest research paper today and congratulate everyone involved in organizing this conference. Creating for the metaverse involves new opportunities for architects and novel uses and activities to be discovered. While some core architectural skills and processes might be applicable to the field, new skills and a shift in mindset and methods is additionally required. To explore the above, an educational intensive one-week workshop was realized at the University of Nicosia back in March 2022, offering the opportunity to undergraduate architecture students to engage with custom software workflows and metaverse platforms towards proposing and constructing interactive virtual environments. We aimed to answer practical questions such as, can CAD software be implemented for the creation of metaverse content? And if so, what are the workflows and limitations involved? What is the potential role and possible applications of computational design tools in creating for the metaverse? In parallel, the research aimed to assess whether the architecture design studio research approach could be valid in a virtual context and capable of producing results justifying further study and exploration. The workshop was hosted under the Architecture Catalyst course in the Department of Architecture of the University of Nicosia in Cyprus. A specific workshop ran during spring semester 2022 and was attended by 13 third-year undergraduate students studying at the Department of Architecture, divided in 5 teams. As part of the workshop, the participants were voluntarily asked to submit their proposals to the Next Top Metaverse Build competition, which offered the opportunity to pitch and test ideas in front of industry-leading metaverses, protocols, organizations, and investors. 2 proposals were submitted at the competition and both got awarded. The workshop brief was structured so that the participants could work in 2 parallel directions: accumulating sufficient theoretical background knowledge and developing a practical software skill set enabling them building for the metaverse. Similar to a design studio research assignment, the participants were initially tasked to analyze their virtual metaverse sites, identify their key characteristics, and register relevant metrics and data for the predominant activities and uses. The students were requested to pose and answer questions such as, who is the target audience? What are people using the platform for? How do users interact? Finally, students were given key readings to consider, attended lectures from specialists in the field, and were introduced to and discussed fundamental concepts relating to the domain. We have realized early on that online 3D modeling tools offered by various metaverse platforms are currently limited in creating, editing, and optimizing builds. As a result, we pose the question of whether CAD software can be implemented for the creation of metaverse content. We chose Rhinoceros 3D and the graphical programming editor Grasshopper by Robert McNeil and Associates to test the paper hypothesis, as these are the software that our students are more experienced with. To streamline the process, we prescribed 3 pipelines associated with specific file types within which the workshop participants could research and develop their projects. Each team selected a pipeline and was requested to visit the corresponding metaverse platforms and familiarize with their technical features, requirements, and limitations. In parallel, students were asked to develop a consistent information workflow to transfer their designs from Rhinoceros 3D to the corresponding metaverse platform, effectively assessing and validating the proposed pipelines. The process resulted in the voxel, the polygon, and the game engine pipelines, identifying distinct paths to metaverse platforms. 5 proposals were developed along these 3 pipelines. The results include 1 proposal in the voxel pipeline for Sandbox, 2 proposals in the Polygon pipeline for Decentraland, and 2 proposals in the game engine pipeline for Mona. I will continue by briefly describing the 3 pipelines and the corresponding proposals. For the voxel pipeline, geometry was created in Rhino, and Grasshopper and translated through Magica Voxel before imported in VoxEdit, Sandbox's native builder. Game mechanics such as animations and interactions were prepared in GameMaker, Sandbox's custom game design tool. The software enables add-ons such as buttons, weapons, and avatar bots, some of which were incorporated in the design. Under the voxel pipeline, we had one proposal titled Control Shift, a customizable and gamified virtual NFT gallery space that can foster interactions between visitors and engage the audience. The project was designed, adapted, optimized, and tested for the Sandbox Metaverse platform. The concept pertains to the customization of virtual space, and the project represents a shifting gallery made out of different types of block geometries. Some blocks are animated in space, some are portable, and some are fixed. The portable blocks allow for space customization by the user to host other activities or implement specific scenarios in a flexible game-like environment. For the polygon pipeline, geometry was modeled and optimized using Rhino and Grasshopper before exported via a plugin including materials and textures. The model was divided in parts and uploaded as a series of assets into Decentraland's native builder. Interactive elements such as buttons and NFTs were added via the builder. The use of PBR materials enabled seamless transition of textures. The Polygon pipeline was used for developing Lush Proposal, an awareness platform designed to inform, donate, and buy NFTs that benefit environmental development and the preservation of endangered flora, a garden space which is used for gathering, education, and play. The project was designed, adapted, optimized, and tested for Decentraland. The main design element of the proposal are the trees that represent various species. 3D models of the trees can be acquired by the virtual community and populated, planted elsewhere in Decentraland or other Metaverse platforms, therefore contributing to the initial cause, educating the community and preventing further flora extinction. The trees were modeled in low polygon resolution and were generated in Grasshopper using an L system algorithm. MetaMaze is the second project developed under the Polygon pipeline for Decentraland, a gamified virtual space that aims to engage visitors through a maze type of environment. It implements interactive features of real-world escape rooms, such as keys, riddles, and buttons. The project is organized in levels of increasing difficulty, which the user needs to complete to win access NFTs, providing entry to specific social events. It develops upon Decentraland's inherent spatial parameters, such as the minimum height an avatar can jump, the maximum height it can walk over, and the maximum walkable slope, while it implements materiality to trigger the user's perception. For the game engine pipeline, geometry was modeled and optimized using Rhino and Grasshopper, including materials and textures before exported to Unity. A Unity template provided by Mona was implemented to translate the model file into the virtual environment. Colliders, interactivity elements, materiality, animations, and lighting features were added via Unity. Vortex was developed using the game engine pipeline and is a generic exhibition space for built environment presentations. A fractal space that enables the visitor to teleport inside the exhibits to experience one-to-one scale buildings on display. The project was designed, adapted, optimized, and tested for the Mona Metaverse platform. The geometry consists of a singular pathway gallery shaped as a helix. Presentation panels and educational interactive media are placed on the exterior surface of the project. Scaled models are positioned along the central axis of the helix and are accessible through portal links strategically located inside the gallery. Odyssey is the second proposal developed using the game engine pipeline, an allegorical proposal that aims to engage the visitor in a journey of experiences and surprises. The project was also designed, adapted, optimized, and tested for the Mona Metaverse. Odyssey aims to cause extreme spatial stimulation to its users by embracing the potentials of animation and lack of physics in a Metaverse environment. Upon entering the virtual environment, the user has a clearly visible goal to reach, an infinite tower. The journey takes the user from one extreme spatial experience to another through portals shaped as part of that tower. There are strong contrasts between these environments, from open to closed, bright to dark, monochrome to colorful, and static to animated. No matter how persistent the navigation is, the user is unable to reach the infinite tower, denoting the importance of the journey over the goal. In terms of responding to the theoretical framework, all teams proposed and articulated new activities, synergies, and experiences. While some of the projects are founded on existing uses, like galleries or exhibition spaces, they all managed to infuse or complement the proposals with innovative elements, resulting in new ideas and pertinent results. Regarding the technical framework, all teams managed to realize consistent workflows and translate their proposals from a familiar 3D modeling environment to interactive metaverse scenes. Additionally, a number of peripheral areas of focus were identified and explored, such as optimization, computation, interactivity, and the consistent use of materials and textures. The workshop and outcome verifies the appropriateness of CAD software and computational design tools for creating metaverse content. In addition, the results support the classification of the three workflow pipelines proposed by the research team. Finally, the authors support that the resulting proposals present an indicative sample of the applicability of the architecture design studio research process in the context of the metaverse. While we understand that empirical analysis is difficult to be developed, the fact that all teams have responded to the brief by addressing the multi-parameter nature of the problem presents a considerable finding. The research enables key realizations that can be investigated in future work and could turn advantageous for architectural curricula. First, metaverse spaces are inherently exposed to the user, which can enable real-time testing and feedback. Secondly, designing for the metaverse can be selectively disconnected from the complexities of the physical world, which appears to fit the early years of architectural education, aiming to explore and experience essential spatial concepts such as scale, perspective, color, light, and others. Finally, building for the metaverse involves technical discipline, self-auditing and optimization strategies, entailing the enhancement of digital skills and methodologies. We would like to thank the University of Nicosia and Simlexity for supporting the workshop and the research. We would also like to thank the guest lecturers, the guest tutors, and of course all the students that participated in the workshop. Thank you for your attention.